Today we define orthogonal projection, the official linear algebra version of dropping a shadow onto a subspace. The projection PUV is the part of V that lands inside U. The leftover part is perpendicular to U. Let U be a finite-dimensional subspace of an inner product space V. Every vector splits into a part in U and a part in U perp. The orthogonal projection PU is defined by PUV equals U. It keeps the U component and throws away the perpendicular component, like a very specialized garbage disposal. If U has an orthonormal basis, the formula is especially clean, because coordinates are just inner products. With an orthonormal basis E1 through EM of U, projection is just the sum of all shadows onto those basis vectors. Orthogonal projection has 5 standard properties. We will prove only the 4th one here, because apparently viewers deserve homework too. Range is U. Null space is U perp. The error V minus PUV is perpendicular to U. The operator repeats itself, and projection never increases length. The 4th property is the idempotent property. That name sounds like medication, but it just means applying it twice is the same as applying it once. To prove PU squared equals PU, start with any vector V and write its orthogonal decomposition. By definition, PUV is U. But U is already inside U, so projecting U onto U gives U again. So for every V, PU squared applied to V equals PU applied to V. Therefore PU squared equals PU. This suggests a more general definition. A projection operator does not have to be orthogonal. In general, we can define a projection operator by the equation P squared equals P. It means once a vector is projected, projecting again changes nothing. Orthogonal projection is the special version where the leftover error is perpendicular to the target's subspace. The extra geometry matters, inconveniently enough. Now we prove the key approximation result. Orthogonal projection gives the closest vector in U to V. For every U in U, the distance from V to PUV is at most the distance from V to U. And equality happens only for the actual projection point. So the closest point is unique. Linear algebra finally makes a decision. The proof is just the Pythagorean theorem, which is what happens when orthogonality actually pays rent. Compare V minus U with 2 perpendicular pieces. The error V minus PUV, and the horizontal piece PUV minus U. The first piece is perpendicular to U. The second piece is inside U. Therefore the 2 pieces are orthogonal. Pythagorean theorem says the squared distance to U equals the squared projection error plus another non-negative squared length. For equality, the extra non-negative term must be 0. That forces U to be the projection point. So projection is not just a convenient vector in U, it is the unique closest vector in U to V. Next time, QR decomposition. Then we immediately use it for least squares problems, where projection stops being decorative and starts doing numerical labor. Projection is the geometric engine behind least squares. Naturally, matrices will show up and pretend they invented the idea.